Welcome students to the basics of mechanical engineering. Today we'll be starting on the next unit, which is unit 3, that encapsulates the topic of thermodynamics. Now, thermodynamics has been incorporated exclusively in unit 3, and from today onwards we'll be starting with all the topics which cover this subject. Now, before we enter the subject, before we start learning the subject, we have to understand what it is and why we study it. So, what is thermodynamics? Thermodynamics is nothing but the science of heat transfer and its effects. Heat transfer occurs on a day-to-day basis in every object, in everything that we know. And thermodynamics is the study of that. It has its foundations in the basic laws of physics, which govern the principle of energy transfer as well as its conversion from one form to the other. So, take for example, in a cellular level, you have got conversion of chemical energy into heat energy to mechanical energy. Uh, in engines, you have got conversion of chemical energy to mechanical energy. In solar panels, you have got conversion of light energy to electrical energy, and all of these phenomena have got limitations which are based on the principles of thermodynamics. Applications of thermodynamics are in each and every field of engineering and technology. So, at the end of the course, we want you to be able to understand the importance of thermodynamics and its applications on a day-to-day basis. So, keeping that in mind, let's look at some of the course outcomes that we expect at the end of the course. So, for thermodynamics, we expect that you will be able to understand the basic concepts of thermodynamics and apply the concepts of heat and work interactions on different types of models that may be presented to you. Okay, so it's really important that you take your time to understand each of these topics, which are heavily concept based. So thermodynamics unfortunately is quite abstract, a field where even though that you have an innate understanding of what the entire field encapsulates, for you to understand the details of it, to understand what happens on a molecular level, on a macroscopic level, on different types of levels, you require a good grasp on the fundamentals. So, in our time together, we will try to ensure that you all understand the basics of thermodynamics and understand them absolutely well. Okay, so let's look at what you all will be studying in the coming classes. So, regarding the syllabus, first of all, you all will be starting with the introduction to thermodynamics, definition of thermodynamics, which we have already had a look at, different types of thermodynamic systems. So, we have to analyze the systems uh, on a in a manner that enables us to figure out all of these heat and energy interactions. So we have to convert our understanding of what an object is into a understanding which encapsulates these thermodynamic principles. So for us to understand that, we have to understand things like thermodynamic systems, the concepts of thermodynamic system, the concept of thermodynamic boundary and the surroundings, different types of thermodynamic systems, closed systems, open systems, isolated systems, adiabatic systems, homogeneous and heterogeneous systems. So these are in individual systems and are different in as compared to one another, and we have to understand each of these systems. Then we have to understand different approaches in thermodynamics, that is the macroscopic as well as the microscopic approach in thermodynamics, that is the approach or point of view. Then we have to talk about equilibriums, because often we don't look at the process, but we look at the end of the process what happens. So we have to think about the concept of something called thermodynamic equilibrium. Then, of course, we have to look at properties of systems, states, processes, cycles, point and path function, temperature, and then we'll be starting with our laws of thermodynamics. And initially, we'll be starting with the zeroth law of thermodynamics. So, in thermodynamics, instead of 1, 2, 3, we start with 0, 1, 2, and so on and so forth in the laws of thermodynamics. So it's a special caveat which only exists in thermodynamics. Most of the other fields of engineering, if you have the laws, for example, the Newton's laws of equation, you don't have a zeroth law, zeroth equation of motion in Newtonian physics. You have the first equation, the second equation, so on and so forth. Similarly, you have the first law for motion, so on and so forth. Okay, so in thermodynamics, you start with 0, then you go to 1, and then you go to 2. So first of all, we'll be starting with the zeroth law of thermodynamics. Then we'll proceed to the concepts of heat and work interactions. First, we'll look at work transfer, and specifically, we'll go to specific category of type of work transfer called displacement work. Then we'll be looking at different types of displacement work. And so, displacement work in various processes. We'll be looking at the representation on something called a PV graph. Now, in thermodynamics, we often represent our processes on different types of graphs. We have got your PV graph, you have got your TS graph, you have got your pH graph. So all of these concepts will be introduced to you, and initially we'll be looking at the representations of different types of work processes on a PV graph. Okay, then we'll be looking at other types of work transfer, not just displacement work, and the net work done on the system. Now, this net work means the total amount of work and doesn't mean Vodafone, Idea, Airtel, or any of that sort. So we're looking at the total work, that is the net work done by the system or on the system. Then following that, we'll look at the principles of heat transfer. We'll be defining what heat is. We'll be looking at how heat transfer occurs. Then we also looking at something called path function. If you are already paying attention, you all will know what path function is, or you all will have covered a bit of path function in the previous section. So you'll be looking at heat transfer as a path function. Then we'll be looking at specific heat and latent heat concepts. So these are very important concepts that we have to introduce and clarify, just in case you all have not covered this in your previous years of formal education. Then we'll be looking at the first law of thermodynamics, followed by the second and third law of thermodynamics. Okay, so this will encapsulate the entire syllabus of thermodynamics.
So after understanding what we are going to study, it is rather imperative to understand why we are studying things. So let us look at each of the applications of thermodynamics in each and every field, or at least most of the applications of thermodynamics in the fields of engineering which are taught in Don Bosco College of Engineering. I'm a mechanical engineer, so I'll obviously have a bit of a bias. So let's look at the applications of thermodynamics in mechanical engineering. So in thermodynamics, in mechanical engineering, what we do is that we use thermodynamics to help convert energy from one form to another. So we primarily use it as in the example shown. You're using chemical energy and you're transferring it, trying to convert that chemical energy. So you're trying to transform chemical energy into some sort of mechanical energy. All right. So what we're going to be doing is that we're going to understand these different types of processes which help us convert the chemical energy, or specifically convert from chemical to thermal energy and thermal to mechanical energy. Okay, and this will help us to do useful work. At the same time, what we're going to also do is to use the concepts of thermodynamics to transfer heat energy from one object to the other. So that is going to be used in the principles of refrigeration and air conditioning. All right. So this is one of the primary ways of primary application of thermodynamics in mechanical engineering. One is to convert from thermal energy to mechanical energy, and there are vast and numerous ways of converting thermal energy to mechanical energy. And the second one is refrigeration and air conditioning. And it is absolutely imperative for mechanical engineers to understand the importance of thermodynamics, because if you don't, you're going to have situations like this, wherein if you try to push the boundaries, push the limits of thermal design to the maximum, you're going to have thermal failures. And once you have thermal failures, you will have runaway reactions, you will have all sorts of these huge failures. and this all of this can be prevented by our understanding of thermal or thermodynamic concepts, which are going to be covered in not only in basics of mechanical engineering but in classes beyond that. Then we have to look at electronic engineering. Electronics and telecommunication is one of the branches which who have this course of basics of mechanical engineering, and you guys obviously have applications of thermodynamics in your engineering as well. Now a lot of electronic designs have a lot of thermal limitations, so you all are probably aware of the of this image. This image is of an artist rendering of something called the Chandrayaan orbiter. Now, the Chandrayaan orbiter was one of the first moon mission which was done, performed or launched by India, and it was obviously sent to the moon. This had a design life of around 2 years, but it unfortunately failed within 1 year. And what happened is that this failure was attributed to the overheating. Now obviously what happens is that you assume that space is very very cold, which is true, but what happens is that you also have a lot of solar flux. So there's a sun which is there, which illuminates the entire orbiter. At the same time you have got other sources of energy, and also you have got the terrestrial radiation, what is this called. So once the lunar surface is heated up, that too starts radiating heat. Now these two sources of radiation or thermal energy basically cause the various electronics and various systems in the Chandrayaan orbiter to start overheating, and then after this obviously that led to the failure. Now this failure was unfortunately detected, or this problem of overheating was detected in less than 2 weeks after launch of the Chandrayaan 2 orbiter, after it entered the lunar orbit. But at the same time you couldn't do anything, because the designs had certain limitations. Now in case if they had worked on it a bit more, or you had used a bit more data, you had learned the different parameters which are there from past missions, then probably this mission would not have failed so early in its lifetime. However, the overall mission was considered a success because most of its mission parameters were met, but however, it could not, achieve its maximum design life. Then we move to computer science. Obviously, this is a very, very important domain and it is highly linked to electronics, wherein your thermal limitations depend or decide the applications or the amount you can push your entire computer setup to its maximum. Now, most of our technologies is silicon based, and next we are actually actively trying to move the base element to gallium nitride. So gallium nitride, we are trying to move it to this element and move all of our semiconductors to from silicon to gallium nitride. So this is the new domain, and obviously one of the biggest advantages of moving this is moving from away from silicon is the limitations caused by the silicon in terms of your thermal stability. So in this example, you have got somebody trying to overclock a system, and overclocking is trying to push your number of cycles which you can do in a second, or number of operations you can do in a second. So most of your computers, your day-to-day computers, have a limitation of from 1.2 to maximum around 3.5 gigahertz. So they will have a base clock speed of 1.2 gigahertz, and they can speed their or increase their clock speed to around 3.5 gigahertz. But anything beyond that is very very difficult, because that causes a very high conversion of electrical energy to heat energy, and this heat energy will basically destroy any of your systems. Most of the thermal electronics will are designed to shut down if they face too much heat, and that is to prevent damage. So they will even if you try to push it beyond 3.5 gigahertz, what's going to happen is that your entire electronic system will shut down. And obviously this is a limitation, and especially when you want to try to improve the time utilized in each of these operations, you want to try to increase the number of cycles which your clock can, or your system can perform every second. So one method of doing that is something called overclocking, and what you do is that you cool this entire system. Most of the home based system use water, but in some extreme examples such as the one which is shown in the figure is using liquid nitrogen to actually cool this entire setup to very very low temperatures. And even though that you have poured liquid nitrogen, what happens is that eventually the temperatures rise and rise rapidly beyond 120 degrees Celsius. It can even go up to 120 degrees Celsius. And at that point, the moment it actually switches beyond 100 degrees Celsius, most of the systems, they just stop performing. So they have a thermal limitation which is set, and the moment the thermal limit is achieved, they automatically start throttling down. So this process is called thermal throttling, and it severely affects the maximum performance that you can gain out of any setup. So moving on to civil engineering, now this is one of the biggest incidents and biggest tragedies in which happened, which is depicted in this image here. So this is the collapse of the something called the World Trade Centers. After terrorist attack, what happened is that the building collapsed. Now, a lot of people attribute this collapse due to the collision a with a jetliner. So what happened is that the terrorists took over the jetliner and they crashed the aircraft into the building. Now, most of the people attributed this entire collapse to the accident, the primary terror attack, but actually this was due to a thermal failure. So what happened is that as soon as the aircraft took off, it's laden with fuel, and what happens is that this fuel is slowly burnt. It's converted to energy, and specifically kinetic energy. It pushes the aircraft along. So at certain point in time, when the terrorists took over the aircraft, fuel content in the entire aircraft was significant, and when they crashed the aircraft into the building, the fuel was spilled into the entire building. Now this fuel burnt and burnt and burnt and burnt, and that is what you can see, the flames which are here. And what happened is that caused the metal structure, which is part of the building, to slowly soften because of the thermal the entire heating which is taking place because of burning fuel. And as soon as that happened is what happened is that the entire building basically started buckling, because at a higher temperature your materials, the properties changes, the materials start to soften, so on and so forth, and that caused the entire vertical part of the building, the above sections of the building, to force it down and cause it to buckle. And you can actually see that here which is happening. You can see that the upper part of the building is sort of horizontal, while the lower part of the building is remains, it's not horizontal, it's tilted at an angle, while the lower part of the building is still vertical. And that what is happening here is that this has buckled, and that has caused the entire building to basically crash down, and that caused the subsequent failures, and that is the reason why both of the towers collapsed. Okay, so this is one of the biggest example, the most common example of thermal failure in civil engineering. Then this is another example of thermal failure in civil engineering, where your tracks actually don't look like this. It doesn't look like a snake. But what has happened is that the designers of these tracks, the railway tracks, failed to account the expansion due to heating. So at very high temperatures, what happens is that very high ambient temperatures, metals obviously expand, and as they expand, if they're allowed to expand, they will expand linearly. But if you're you hold them in place, for like the way you hold them in place in the case of railway tracks, what happens is they start buckling, and this causes a severe warping of the railway tracks, and this obviously results in a case where you cannot use these railway tracks. In North India, actually, this is quite a common issue, but obviously it's not to this extent. However, what happens is that in places like Gujarat or Rajasthan, where the temperatures go up to even almost 50 degrees Celsius, so what happens is that the road surface basically turns very sticky. Now, what happens on the road is that the road is made of asphalt, which is a sticky substance, which is a product of petroleum. And as it is heated, it turns softer and stickier. So a lot of these road pavings basically turn so sticky that even if a person walks on them, they'll get stuck on that surface, and it's a real problem. So again, this is a design limitation which is caused by the effects of thermodynamics. another really important area of which is concerned or which has real applications of thermal engineering is chemical engineering. And I'm not sure how many of you all will know this company name called Union Carbide. Now, Union Carbide was a company which used to make insecticides. It was located, or it was located in this town called Bhopal. Okay. Now, some of you all may understand where I'm leading this to. Now, this is regarding the Bhopal gas tragedy. So, Union Carbide was a company in question. They used to manufacture various insecticides, and one of the uh, prime ingredients of the entire chemical process was something called MIC, methyl isocyanate. And what happened is that in December, 2nd of December, uh, in 1989 or 1986, if I'm not wrong. Just a second. Yeah, on 2nd of December 1984, what happened is that there was a huge leak of this MIC. It's a very toxic compound, it's a very toxic chemical into the atmosphere. And this was primarily because of poor, poor design choices, poor maintenance practices of the entire firm in question. But the prime reason was something called a thermal runaway. Now, what happened is that in this MIC, which was being stored, there was some water which flowed into the tanks which was there, which the MIC was stored. Now, what happened is that water, when it comes in contact with MIC, it causes MIC to decompose into a different compound, and it also releases carbon dioxide. Now, this process is an exothermic process. It is that means it generates heat, and as soon as it generates heat, it causes the acceleration of this process. And so there's as water was being leaked into this tanks of containing MIC, the entire you know most a significant portion of the MIC was being decomposed into carbon dioxide and another product, and also releasing more heat. Now, that's accelerated the process and increased the tank pressure. Finally, what happened is that the tank could not sustain that, and a safety valve was opened. Now, this safety valve caused the leakage of MIC into the atmosphere. It should have passed through different systems which prevented the leakage of MIC into the atmosphere. But because of certain maintenance practices, bad maintenance practices, and bad choices, they were all not functional, and a significant portion of the MIC was leaked into the atmosphere, and that caused lots of deaths, and unfortunately, a lot of long term damage as well. So again, in chemical engineering, thermal control is absolutely key. So as you know that we have looked at different types of examples, different types of engineering examples in which uh, the limits of thermodynamics are very important, or the knowledge of thermodynamics is very important to understand certain limitations or certain issues that you may face. Okay. So it's absolutely important for each and every one of you to understand the concepts which are going to be taught in in these subsequent classes, and ensure that y'all don't limit yourselves to just your domain, because as soon as you graduate, y'all will be faced with a lot of cross domain scenarios, which is as is popularly known. One scenario which comes to mind is in the case of uh, this happened quite a few years back, and I believe I brought it up during the orientation for basics of mechanical engineering. And what had happened is that there was a oil filling process which is happening in some other country, and this was remotely controlled by some other centralized server. Now, the server was undergoing some sort of maintenance, and a person in charge of maintenance accidentally reset one of those variables. Now the variable, basically what he had reset was the counter of how much fuel had actually been loaded. Now if you reset it to zero, it doesn't mean that actual whatever has been loaded, the fuel that was loaded into oil tanker was actually zero. So what happened is it started overflowing, and it caused a lot of damage, or not just environmental but financial as well. And this is a real problem. So you have to understand that your knowledge is not just limited to your domain, which you, if you're a civil engineer, it's civil engineering, if it's computer or electronics, it's computer and electronics, or if it's mechanical, it's mechanical. The world out there is all cross domain. So you have to have a knowledge, basic knowledge of different types of domain for you to be able to function as a as an engineer in today's world. So for example, I myself was a maintenance engineer in when I was working, and at that point of time, I had to have a knowledge of electronics. I had to have a knowledge of computer science, and as well as a bit of civil engineering as well. So I had to use all of these concepts in my day-to-day activities of maintenance. So please do not take this subject very lightly. It is very interesting. It's also very important. Okay, so in the subsequent classes we'll be diving deep into these concepts of which we have mentioned in the syllabus copy, and I hope that you take your time, the allotted time, quite seriously. Please try to attend each of the classes, and if you all have any doubts, please ask them to your concerned faculties. Okay.